Welcome everyone to Protocol Labs' research seminar series. It is September 1st, 2021, and we have Emanuele Giunta presenting his work titled Efficient and Universally Composable Single Secret Leader Election from Pairings. Emanuele received his master's in mathematics in 2020 under the supervision of Professors Dario, Catalano, and Ignacio Cascudo. Currently, he is pursuing his Ph.D. at IMDEA and continues working with Professor Cascudo. Emanuele studies zk-SNARKs, multi-party computation, and functional encryption. Thank you so much for joining us today, Emanuele, and I'll let you take it from here.
Thanks for the introduction, and thanks everyone for having me here today. So today, in the introduction, I'm going to talk about our research on this primitive single secret leader election, which, by the way, was first proposed by Protocol Lab itself a few years ago. So without further ado, I'll just start with a quick overview of what we will discuss today. So first of all, I'm going to introduce the problem, essentially what a single secret leader election scheme should be, what is the goal that it tries to achieve. Then I will introduce a few preliminaries, like essentially the definition of functional encryption, which I think it's well known to everybody, but I'd still like to reintroduce it. And then more specific kind of functional encryption schemes, like the predicate encryption keyword search functionality or the orthogonality functional encryption scheme that we will present later. Finally, after the preliminaries, I'll introduce our construction and then compare it with previous constructions. Essentially, since this primitive was introduced, this problem actually was proposed a few years ago. There are not so many previous construction to compare with. Essentially, only one paper has been published before. And we will actually compare with that, both in terms of the security level we achieve and the communication and state complexity that we get. So first of all, let's introduce what a single secret leader election scheme should be. So the idea is that given a set of users, you could think them as, for instance, node in a blockchain context, context, and for instance, they want to produce the next block. This protocol essentially tries to elect secretly one of those users, making this user the next leader. And the next leader is hidden from the other until he decides to reveal himself. So just to make an example, in theory, we should have like this protocol represented as a black box. Parties at some point request to the black box to elect a new leader. The black box randomly decide who is going to be the next winner, and most importantly, other parties have no influence on who the next winner is going to be. The next winner is not revealed until she decides to reveal herself. And once she reveals herself, the protocol tells the other that the winner of the election that they requested was indeed, in this case, the player with ID 3. Okay, so to more formally define what this protocol should be, we have three properties. Essentially, those are the properties introduced by Bonnet and Aliter and other people previously. So the first property is uniqueness. And it says essentially that each time we perform an election, only at most one user can be the next leader. So going back to our previous example, only one leader was, only one person, the person with ID 3, was chosen to be the next winner. All the other receive a lost message in this case. So the first property tells us that at most one user should be the next leader, but unfortunately it cannot tell us that every round we always have a leader that eventually reveals herself. This has to be the case because, for instance, if a malicious user actually wins an election, I mean, there is no way we can force a malicious user to reveal himself. He can decide to disrupt the protocol to just, he can just decide not to reveal himself. The next property is fairness, and essentially tells us that honest user win with the right probability, meaning that again meaning that essentially the next leader is roughly chosen randomly among all the users currently registered. This definition has a few implications. So, for instance, it tells us that any adversary that corrupts a certain amount of users, it can actually, it will win only with probability related to the amount of users it's corrupting. So if it's corrupting T users, it will win with probability T over N. This tells us also that an adversary cannot alter the probability of other honest users to win. So again, going back to our example, an adversary cannot reduce the probability of a certain user, for instance, the user with the D4, to win. The winner would be essentially uniformly random among all the users currently registered. And finally, another thing that this property is not telling is that also the dishonest user will win with the right probability. This is actually false for a certain amount of reasons. For instance, we have that, for instance, if an adversary is corrupting T users, you could produce like fake registration or malformed registration for those users, or in general can misbehave during the protocol, so that this user will actually never win. This is something we cannot avoid in general, and we actually don't even try to do that because we just want to preserve the winning probability of honest users. And finally, there is the unpredictability property, which is arguably the most important. We want that until the leader reveals himself, no adversary has any information about who is going to be the next leader. So essentially, this property addressed this the time between the instance in which the protocol tells the user with a D3 that she won, from the moment that the user actually reveals herself. During this time, no one has any information on who was actually the winner of the current election. Just to quickly mention them, there is actually the first one is based on indistinguishability obfuscation, and it's mainly presented for theoretical reasons, since even though it may seem now that indistinguishability obfuscation is possible, it's still a very expensive primitive to use in practice. The second one is based on threshold fully homomorphic encryption, and also rely on assumption on lattices, and is not extremely efficient. However, it's more practical than the first one, and even though since it's a threshold encryption scheme, essentially it also requires that a certain amount of user is honest, and also has a certain amount of constraints. Actually, the amount of user has to be a power of 2, so it's kind of a limited scheme. And the last one, which is the most practical they present, is essentially there are actually two constructions based on the decisional deferment assumption. Okay, and this is arguably the most efficient solution they present, but it's still it's very expensive on communication and on state efficiency. So for this reason, we introduce our protocol. And first of all, we begin by giving the definition of some primitive that we will require to introduce our construction. So the first primitive is essentially functional encryption. So functional encryption is essentially a generalization of public key encryption, with the only exception that each time we have a key generation algorithms that, given a function, give us a functional key. And each time we encrypt a message using the functional key, instead of decrypting the message we received, we can decrypt abstract a function of the message encrypted. So actually, well-known functional encryption schemes, for instance, are one for inner product that returns the inner product of a secret vectors and the message, which is also a vector in that case. And there are other examples. One example that I will need now, the most basic probably, is the keyword search functionality. Essentially, the functions that we use for our encryption scheme are that we can call them the delta function. Essentially, those functions compare if the input equals a given message in the element in the message space. So in this case, given a functional encryption scheme for these functionalities, what we can extract given a functional key is only if the ciphertext, in this case X, equal Y. So we can only make these kind of checks. For those who know about anonymous identity-based encryption, these two primitives, essentially keyword search functional encryption and anonymous identity-based encryption, are essentially the same things up to minor changes. So just to make an example to make things a little bit more clear. In this case, we assume to have a message space of 1, 2, 3, 4. We are given a secret key labeled with the element 3. And given two ciphertext, one decrypts to 0, and the other one decrypts to 1, meaning that in the first case, the message encrypted is not equal to 3. And in the second case, it is equal to free. So the only information that we learn is that in the second case, the encryption, the ciphertext encrypt exactly free, while in the second case, we learn nothing besides the fact that it does not encrypt free. A generalization or a different functional encryption that we could present, still along those lines, is that for orthogonality functional encryption. In this case, the functions that we consider are not performing equality checks, but rather return the predicate of whether two vectors are orthogonal or not. So in this case, functions are labeled with a vector y. And essentially, given an input x, it returns 1 if the two vectors are orthogonal, and 0 if they are not orthogonal in this case. The only information that a user with a functional secret key can learn from a ciphertext is only if the labeled vector is orthogonal to the encrypted vectors. So in fact, PKC and orthogonality functional encryption schemes are tightly related, since one can realize keyword search functionality from the orthogonality functionality. Indeed, the idea is essentially that given two elements of a vector space, FQ in this case, of a field, alpha and beta, we can define two vectors, x alpha and y beta, essentially as alpha minus 1 and 1 beta. And the key idea is that if we can check whether or not these two vectors are orthogonal, we can essentially derive if alpha and beta are the same. This also, again, trivially because these two vectors are orthogonal if and only if alpha and beta are the same. So the idea is that now that using an orthogonality functional encryption scheme, we can realize a PKS scheme. And this immediately, at least in an idealized world, would yield us a basic solution for realizing SSLE. Okay, so the idealized solution would be more or less along these lines. So each user is given a secret key associated to his identity. So user I received the secret key associated to I. Those are secret key for a keyword search functional encryption scheme. The idea is that there is, in theory, again, this is an idealized protocol, there is this black box that when we request to produce an election, when we request to perform an election, it returns randomly the encryption of one of those identities. In fact, how to realize something like that, how to generate the random encryption of a random identity is probably very hard. In fact, it is very hard. But assuming that we can do something like that, then the idea is that only one of those users is able to decrypt the message given. So all the other users besides the user free, while attempting to decrypt, receive garbage. Indeed, actually, according to the definition I gave before, decrypting they receive 0. And the winner is the only one who is able to decrypt the message to 1. So the idea is that in order to prove that she actually won, she could, for instance, return a non-interactive zero-knowledge proof that she's able to decrypt the ciphertext to 1. This solution, however, has a few limitations. The most important one is that it's very hard to produce this random, the encryption of a random message in a very small space. So there are two ways to overcome this issue, one of which is not really practical anyway. So the first solution in theory to overcome the fact that it's not easy in general to produce this kind of ciphertext encrypting a random message. The idea is that we could in theory hope to have a scheme that has a polynomially small plain text and it is dense, meaning that we can, given fresh and public coins, we can produce an encryption of a message and this encryption is essentially the same as encrypting a message with private coins. So this is a very strong requirement. I don't know about any such scheme, even though given any scheme with those properties, we could immediately realize an SSLE protocol is extremely efficient one. Our solution instead is to relax the way this black box behaves, so that it's easier to realize in practice. Keeping in mind that in our case, we really want to reduce both the number of rounds required to produce this ciphertext and also the amount of communication required to produce it. Because again, using multi-party computation, in fact, we can produce a ciphertext with those properties. Again, a ciphertext that encrypts a random identity among all the user currently registered. but that would be significantly expensive from generic technique. So in order to relax the behavior of the black box, we introduced new functionality. Indeed, it is the modular keyword search functionality. So instead of actually just checking if the given element X equals the labeled element Y, we check something a little bit, we check something easier. In fact, we check if X and Y are equal modulo N. So this definition might look a little bit cumbersome, but it's in fact just checking if X and Y are equal modulo N. This is like the multiple of N that their difference has to be equal to. And there's also another little constraint here that this variable delta has to be small. This K is a parameter of the scheme that we are using. It's fixed. And in our case, it's going to be like very small, approximately of the size of the logarithm of the number of users in the registered. So the issue now is how can we realize this new functionality, and why this new functionality help us in realizing a secret single leader election scheme. So the main idea for realizing this new primitive modular PEKS from orthogonality functional encryption scheme is to observe that this equality is essentially the same as testing that these two vectors are orthogonal, which is something you can do efficiently through this orthogonality functional encryption scheme. And the idea now is essentially that to encrypt this message, X and N, we just encrypt the vector on the right-hand side. And in order to give a functional key, we just give functional keys for the orthogonality functional encryption scheme associated to the vector on the right-hand side for each delta in from 0 to kappa minus 1. So given all these secret keys, the idea is that we check for all of them if the decryption returns 0 or 1. If we found at least one of those vectors that is orthogonal to the encrypted vector, we know that this equation on top holds. So X and Y are equal modulo N. Just to fix areas, I will just briefly sketch how this modular PEKS could be implemented again in the toy solution we presented before. This time, each user is given again a set of keys and not only one. This is due to the way we actually realize the PEKS, the modular PEKS. So each user is given a set of keys. And each time they request an election, the black box returns the encryption of a random message. But this time the message has to be distributed in a more relaxed way. Indeed, it has to only be distributed over the range from 0 to k times n, where n is the number of users. And we only require that x is uniform modulo n. Just to look ahead to what our construction is going to be. If x is the sum of several elements, all in theory uniformly random over n, then we know that x is also uniformly random modulo n. And in that case, given an element that is the sum of several elements uniform over that range, it is in fact enough to have only one of those elements uniform over the range from 0 to n minus 1, where again, capital N is the number of users. So, the idea then would be that we have a small committee that choose these addends that will make X. And as long as only at least one of those members in the committee is honest, so that at least one of those elements is uniformly distributed, then the sum is also uniformly random modulo n. Anyway, for the moment, just stick with this simplified solution. So we are encrypting an element X that belongs in this larger range. In this case, for instance, let's pick 7. So again, the number of users is 4. So, and we fix, okay, I didn't say that, but we fix kappa to be equal to 2. So in this case, belongs to the range. And while when all the users try to decrypt the message, the only one who is able to decrypt, to obtain 1 while decrypting this message is the user with identity 3, because 3 and 7 are equal modulo 4. That's the basic idea. So now let's look inside the box to see how we actually realize this magical box that returns random ciphertext. Now I actually need to give a little bit more details on how the orthogonality functional encryption scheme is given. In order to give a practical and efficient construction, in our paper, we actually propose a new orthogonality functional encryption scheme that is based on previous work of Wojtek in 2018. And it's based on pairing and the symmetric Diffie-Hellman assumption. Essentially that DDH holds both in G1 and G2. Okay, for those who doesn't know that, essentially a pairing is just a bilinear map between two groups and a target group. Okay, again, prime order groups. And indeed, the scheme we present is extremely efficient. Both the public key and the ciphertext are all smaller than 5 elements, 5 group elements, which is indeed it's actually better than the construction presented in the paper of Wojtek, but the reason is that we are not targeting high level of security. Indeed, we just target selective security. And the reason selective security is enough is because we are encrypting random messages. So just to recap, selective security essentially tells us that in the IMDEA game, the adversary that makes the query to that makes an encryption query at some point has to perform this query before the master public key is given. So the two messages have to be independent, which is in this case is not an issue, but in general this is a strictly less stronger security notion than general in CPA. In our case, just to begin with, we need to produce an encryption of a message of a given shape. Just to pin everything down. So the encryption of a message, in this case, a vector that is of the form m minus 1 and minus n, in our scheme has the following shape. Now, I won't require you to remember actually during the construction these exact definitions. So just to simplify things, we only need to know that there is a term. Okay, let's just go back. There is a term, essentially the first one and the last two, that linearly depends on a randomness S. So there are two terms, essentially the first one and the last two, that linearly depends on a randomness S and another randomness sigma. And then there is the second term that essentially depends quadratically in this case on sigma and on m. So what I require you is just to remember that there is a block that depends linearly on and also on times another block that depends linearly on S. So what we need to recall is that it's simply that the encryption of a message of that shape depends essentially linearly on S and sigma, except for this block. In order to produce a random vector, the encryption of this random vector, where m, okay, I'll tell later what the distribution m should be. We actually need the last primitive. The last primitive is threshold homomorphic encryption. It is a scary way to say actually that we are just using Elgamal. And it is essentially an encryption scheme that supports homomorphic operation, such that essentially that the encryption of two messages, the product of the encryption of two messages is essentially the sum of those two messages. We can exponentiate to field elements, and also we can multiply by given group elements. And those would be the sum. Okay, in this case, those elements, just mix the notation. Those elements belong to the field, while those elements belong to the group. Okay, so okay, in this case, we also require threshold homomorphic encryption. The threshold parts comes from the fact that we assume that there are at least T+1 honest users, which are able to decrypt a message, and also that the dishonest users are less than T, because in these kind of schemes with T privacy, less than T user or T are unable to decrypt or gain any information about the encrypted message. So in our construction, essentially, we use Elgamal, where the secret exponent is T shared among the users. So just to give an example, so for instance, if we assume that half of the users, more than half of the users is honest, we can fix T to be essentially half and half rounded down to the lowest integer. everything, I've introduced everything, so we can go ahead and see how the election protocol should work in practice. First of all, we have this open box, which essentially represents a random beacon, which is a primitive introduced in several recent papers, but can also implemented in practice in several other ways. For instance, through the random oracle model by taking the hash of some given public state, or in several other practical ways. So essentially, this random beacon, while each time we request it, it returns essentially randomness. And in this case, every time we want a new election to occur, we query the random beacon, which returns the encryption of a random sigma. This is possible essentially because ElGamal is a dense encryption scheme, meaning that if we take two random group elements, we can always interpret them to be the encryption of some message. Of course, given a public key, and I mean, we assume that the setup has happened before. Okay. So the first step is to query the random beacon to return the encryption of a given element sigma. And next, we also request the random beacon to select among all the users currently registered in the protocol to select among those users a subset, a committee of small size, roughly the logarithm of the number of users. And this committee is in charge to produce the next ciphertext. So user in the committee essentially takes a random element M1 ranging from 0 to the number of users, and a randomness S1, Si, that is a random field element. So each user selects randomly these parameters, and using the encryption of sigma, and using essentially the linearity of the homomorphic encryption scheme, this locker here, they can produce essentially a share of the right encryption, even though this share has to be encrypted under the threshold homomorphic encryption scheme. This is important because in this case, I mean, if we are not encrypting, okay, why this is important? It's important for two reasons. The first one is that we are essentially cheating here. Instead of computing the product M1 times S times sigma, we are using the same sigma for everyone, so that we can essentially say that the encryption scheme is essentially linear in M1 and not quadratic anymore. This, however, has a cost, and the cost is that now the share that each user is giving away are encrypted under a threshold homomorphic encryption scheme. So anyway, since this encryption scheme is homomorphic, we can actually take the product of all those shares, and taking the product, essentially we can take we obtain essentially a ciphertext of the right side shape, where S and M are essentially the sum over the sum of all the Si and the sum of all the Mi. So the last step that we require is the most expensive, actually, in terms of communication, and we require to decrypt using the threshold homomorphic encryption scheme to decrypt this ciphertext and essentially get back the challenge ciphertext that we required. This is essentially what we wanted to get in the first place. So in the toy solution, this is what the black box was giving essentially for free. In this case, we had a few costs to pay, essentially a threshold decryption and actually small communication, essentially coming from the operation performed by the users in the committee. So this protocol essentially has a few properties that are interesting in our case. So the most important one essentially is that the resulting element M in the ciphertext that we return is the sum of k different terms, and assuming that at least one of the users in the random committee that we chose in the first place, assuming that at least one of those users is honest, we know that at least one of those M is uniformly random modulo n, which implies that their sum is still uniformly random modulo n, which is essentially what we needed to have a working, in our previous toy example to make it work. Okay, so that's essentially what we needed. So the last things I need to talk about is just how registrations work. Maybe I'll actually talk about that later. Actually, there is still something more I forgot to mention. So in this protocol, there are also some trade-offs that we can take between efficiency and security. And they essentially comes from the fact that we can choose either a small committee for practical security or a larger committee for achieving 80 bit of 80 bit of statistical security. So in fact, in our paper, we show that if we take a committee of sites log n, this still provides concrete security, even though does not achieve 80 bit of security as in theory one could aim for. Conversely, if one wants to achieve 80 bit of security, for instance, in the case of honest majority, it's sufficient to take a committee of size 80, which is still small compared to the size of the number of registered users, which can be as large as 2 to the 14 or even more. I mean, depending on how the system is going to scale. So the last thing I need to discuss about is the registration. So how do we let new user join our group? So in dynamic settings, which is always the case in blockchain, we want new user to join the group and to be able to be elected. So we need a way essentially to give new users their secret key. Registration are also used in the setup to give when the protocol begins to give each user each secret key. So it's not only for dynamic settings in general, even in static settings for the setup, this is a required part of the protocol. So registration in theory should work, just to give an example of how it should work in theory. So a new user should query this other black box to perform a registration. The black box should give the new user a secret key and assign it to him an identity, and should give to the group of users previously registered the identity of the new user. So, this is something wrong, sorry. So just to go back to our orthogonality functional encryption scheme, in this case, this means that we need to produce the secret key of the new user. The secret key is essentially the last term, and also we will discuss briefly how to produce them in the setup, the master public key that is required to make the encryptions. So observe that our orthogonality functional encryption scheme is actually quite easy and almost linear. I mean, it cannot be linear because otherwise some attacks could be launched against this primitive. However, it's almost linear in the sense that given R, the secret key is linear in W. That is something that has to be secret. And also given the vector A, the master public key is again linear in W. So again, we need to produce these two elements, the master public key in the setup and the secret key each time we register a new user. And the only thing we need to remember is that the master public key depends linearly on A and on the product of A and W, these vector and matrices. And the secret key depends linearly on R and on the product of R times W. First of all, let's see how the setup works. So each time we want to set up a new group, we essentially choose a small committee again. Actually, forgot to place the arrows here, but yeah, the random beacon is queried, and it chooses a small random committee of 80 users, in this case, for instance, or in general, a small committee, and essentially gives away a random element, two random elements in this case, which we interpret as the exponentiation of the generator of the first group to the power of a vector A. Each user in the committee, on the other side, picks random matrices Wi, and in the end, what we want to have is that these elements Wi are the share of the final W. So what they do is they take the given element returned by the random beacon, and they exponentiate it to the Wi that they get. And using the fact that essentially all the operations that they have to perform are linear, they can return the shares of the master public key. So since A is fixed and it's the same for every user, user can now multiply all the shares that they produced, and essentially they get back both the shares that they returned, and the product, which is the actual master public key. Next, assuming that a new user wants to join and ask for a new secret key, what we do is that we use the same committee as before, which knows the share of W. This is important to produce the secret key indeed. The user queries to the users in the committee to essentially produce a new secret key. And each time he makes a register request, the random beacon produces a randomness R. This R, just remember, is the randomness figuring in the secret key. And now that R is fixed for everyone and public, this might sound dangerous, but actually in the paper we show that giving away these elements is not dangerous and does not affect security. Okay, so given this element publicly, they perform a linear operation using WI, their share of W, on R, and produce the share of the secret key, those shares here, which are secretly given to the new user. And the new user essentially takes the product of them all and privately returns the secret key. That is, again, the product. And it's in the right shape. So there is something I haven't mentioned so far. So essentially, the protocol I've described now is assuming passive security and actually honest but curious adversary. In theory, we should also have some expensive, sometimes expensive, in this case would not be so much expensive, but I mean, it's still an extra cost. So we could actually add zero knowledge proof to ensure that users in the committee perform the operation correctly. And they're not trying to disrupt the protocol. However, there is something that we don't need any zero knowledge at all in order to be sure that their users are performing the operation correctly. And this is to check that the secret key shares are correct. Indeed, this comes from two nice facts of our orthogonality functional encryption scheme. And the first one is that user can essentially check if a secret key is correct, essentially by checking if they can encrypt at 0, if the secret key they receive is able to correctly decrypt 0. Observe actually that 0 vector is orthogonal to any vector. So each time you decrypt 0, you always get 0. You always get 1, meaning that y is orthogonal to 0, which is always true. And actually, if this process, if this process actually return 1, this means the secret key is correct, meaning that it behaves in the right way. And this is the first nice fact. And the second one is that the master public key share and the secret key shares, which just to remember, each user has actually access to the master public key share of the users in the committee and the secret key shares that he receives. This pair essentially defines an orthogonality functional encryption scheme by itself. So user can check for each share if this share is correct, and in case it's not, they can just perform actually a complaint round where they complain that a secret key share was not computed correctly. And of course, this also means that the users is somehow penalized and the share are ignored. In conclusion, now ready to give essentially, we can actually compare with previous works our construction. So as I said before, the most practical one is the one based on DDH and shuffling. So just to give a quick overview of how it works. So essentially, in this construction, each user at registration time publish the encryption, the Ergon encryption of 0 through some randomness that only he knows. And there is therefore this long list of encryptions given by each users. And at every step, this list is shuffled so that no one has any information of which ciphertext belongs to who. Each time the random beacon is queried to return a random element, which essentially points a position in this long list, and essentially picks a random ciphertext from this long list. And the only user who is able to decrypt this ciphertext is the next winner. This solution is probably the most efficient one, and still the shuffle-based one at least requires a state size of O of n. And this is the case because each time we perform a shuffle, we need to keep the list of ciphertext in the state. Actually, in their paper, they also presented a more efficient but less secure version, where they essentially shuffled only a subset of those ciphertexts of size square root of n. And okay, of course, and clearly the solution has a smaller state size and smaller communication, but again, also smaller, it achieves weaker security guarantees. Moreover, there is also another downside on the shuffle solution, meaning that if we want to register k new users instead of only one, we need to perform k shuffle. Essentially, each new user has to shuffle the list at least once in order to be sure that his own ciphertext is securely hidden among the ciphertext of the others. And this number of rounds, this I-round complexity actually can be even doubled. As in their construction, they present a variance in which no interactive zero knowledge at all is required, but there is a complaint round in which every time the shuffle is performed incorrectly, user complain that the shuffle was actually incorrect. So the shuffle-based solution has essentially two downsides, meaning a high state size and a high round complexity in registration. And our solution instead is able to reduce the state size from linear or general square root of the number of users to polylogarithmic in the number of users, and achieve also a constant round complexity for registering a large amount of users.
Emanuele, can I ask a question here?
Yeah, sure. Actually, I cannot see the. Okay, sorry. Go ahead.
No worries. Can you tell me again why the state size can be less than n?
Okay.
Essentially, size, because maybe you mean the size of the. Yeah, exactly. What do you mean by state size?
Okay, yeah, I think that's essentially something I should have specified before in this discussion. So by state size, I mean, okay, actually assume that all the users essentially don't remember anything that was sent throughout the protocol. The only thing that they remember is their secret key and nothing else. So every information that we want to be used in other rounds has to be kept in this state. So in this case, in practice, you can fit, for instance, this is essentially the main chain, while the communication actually refers to like maybe off-chain communication complexity. So maybe that's actually our model, and it's essentially the same model as Bonnet, roughly. Of course, like if every message we send has to be placed in the state, then it's of course impossible to achieve a smaller state size than the communication complexity. Okay. However, another way to justify why the state size can be smaller than n, essentially, if the state size are the messages placed in the chain, essentially the new leader that create the next block can essentially compute functions of the message sent in the current rounds and only place aggregate data, for instance, instead of just the whole thing that was sent. And in our case, indeed, the only issue is that, I mean, the most expensive and the only expensive step is the threshold decryptions that require O of T communication. But we are able to aggregate all the decryption shares and only post on the chain just a few group elements. So that's essentially what I mean by low state complexity. Okay, so this is about asymptotics. Actually, there is also a downside. So our work is not actually perfect. So there's still improvements can be achieved. So in practice, even though the communication complexity is asymptotically as large as the shuffle-based solution, actually, in practice, the communication is roughly 2 times larger than the shuffle-based. And of course, it's like larger than the shuffle based on the square root of n. This can be decreased, assuming, for instance, that a large amount of user wants to join the group. Because in the long run, essentially, the high communication complexity required to make elections essentially becomes smaller compared to the complexity of adding k users to the group. When k is large, for instance, the logarithm of n. Okay, but that's something that really depends on the practical scenario in which these protocols are deployed. And finally, I have a slide on the security guarantees required in each construction. So essentially, in the Bonnet scheme, the definition I gave before is the one introduced in the paper by Bonnet and others. And essentially, they define a game-based definition for SSLE. And their construction essentially achieve the game-based definition unless the shuffle, the square root of n shuffle-based solution, which is like weakly unpredictable, meaning that the adversary has more information on who is going to be the next leader. However, their construction is based solely on DDH, which is a well-established assumption. So that's the upside. On the other side is that we actually define a new security notion for the SSLE, that is the universally composable definition, meaning that actually this definition stays secure even if concurrent or parallel composition is performed. So several instances of the same protocol are performed, or maybe the protocol is interleaved in arbitrary way with other protocols. The scheme remains secure, even though this is not still active security in the UC model, but it's just passive security. A reason why this cannot be active security, it's because, for instance, we are choosing a random committee, and we hope that at least one of those members is honest. If the adversary is able to actively corrupt users, can simply corrupt all the users in the small committee and disrupt entirely the protocol. So our solution is far from being secure in the UC model against an adversary who perform active corruption. And that still remains a challenging open problem, I think. Okay, so I think that's all. So thanks for your attention so far. And I'm ready to take more questions if you have any.
I have a question, which is, what do you think is stopping this for being used in practice? Or do you think the main, either if you think it's if the constants are good enough, or if there are other open problems that we should look into it next?
So what's limiting this to be like practically usable?
Yeah.
Essentially, I think, okay, since our construction essentially behaves better, I mean, I guess at least we think than the shuffle-based solution. I mean, actually, I have no competence, I'll be honest, to say if something is practical or not, since I mean, mainly focus on theoretical issues than actually practical, so I apologize for that. Currently, the only issue about our paper, I mean, our work, something that could be improved. The only issue, essentially practical issue, is that our setup is a little bit expensive in terms of communication. Yeah, so just to make an example, I mean, actually, I mean, again, I'll be honest and say that I don't know if those are like practically impossible or practically achievable parameters. But for an amount of users that are around like 2 to the 14, we measured that the setup amounts to roughly 1 gigabyte of communication among all the users. However, like the state complexity is already lower. So if it's expensive to add messages to the chain, rather than just communicating messages throughout the network, then in that case, our construction, I think, becomes more practical than the previous one, because only a few megabytes of information needs to be added every time an election is requested.
This is very interesting work. I'm very curious on, I think that anything that is in the order of higher than kilobytes for blockchain purposes may be already like a no-go. But I think that there may be like practical. So yeah, in the same way with the Bonnet paper, we took some shortcuts by, I don't know, doing a shuffle on a subset, or so maybe there are some shortcuts even here to make some of the ongoing communication practical. I would be very curious to understand more the details.
So just for clarity, so you referred to actual communication, right? Or
so, sorry, I meant both the state and the communication. I mean, at some point, even You mentioned order of gigabytes or an order of megabytes for ongoing.
For the communication and the state size, right?
Yeah. And I think we're talking about like large them. For communication, I expected that it's the way this communication works is through a message on the chain, unless there is a parallel protocol where they communicate with each other. And depending on which direction you took, I think you still have you can transfer. This is meant. I mean, it depends how you integrate this in the consensus protocol. But say that we want to run this every block, then there is a limited amount of data that you can communicate in 15 seconds.
So actually, I don't even know like how much time usually like is is allowed between two different two different blocks in this context. I'll be honest. Anyway, since you were mentioning shortcuts that are possible, indeed there are some, even though they might imply like that the round complexity is a little bit higher. There is something that we discussed, but then decide to not include in the new version of the paper, which by the way is not even online yet, but it's going to be soon. So essentially, again, the only expensive step is in the threshold decryption here, where we require all the users, at least T users, to decrypt. Indeed, there is another way. So since all of this, all these messages encrypted with the threshold homomorphic encryption scheme are re-randomized by the users, those users know the randomness. So if all the users decide to, if the user behaved honestly, they could in theory aggregate the randomness they used and decrypt this, remove the threshold homomorphic layer and obtain the new ciphertext without requiring the threshold decryption. However, the issue is that if any of those users decide not to cooperate, then the actual threshold decryption is required. This essentially means that there is an extra round that is in which nothing essentially happens. So, but yeah, I think it depends like if one wants to leverage like communication complexity or random complexity, I think, yeah.
Would it be fair to say that the shuffle-based SSLE works well when the quorum changes frequently, whereas your protocol works better when there's long-lived epochs when participants don't change?
I would say it's more like, okay, actually in our protocol, user may change often, and not even change. It's more like new user can enter the group often. And in that case, our protocol is essentially way better than the shuffle-based. On the other side, however, if the whole group change often, then as you say, it's right. The shuffle-based solution is more efficient than our protocol, essentially because we need to run again the setup from scratch and not register a new user.
All righty. Thank you everyone for joining us today. We hope you learned a lot. If you're interested in hearing about future talks, funding opportunities, and more, make sure to sign up for our mailing list, which can be found in the description below. Also, please take a look at the website grants.protocol.ai to see our numerous open grant applications. And finally, if you're interested in helping us move science forward, please click on the Lover link in the description below to see all of our current job postings. Thank you again, Emanuele, for your great presentation, and we hope to see you again soon.